Let us look at the resting membrane potential. Now we know the cell membrane divides the outside of the cell ECF and the inside of the cell ICF. We have got different ions inside of the cell and outside of the cell. Most prominent ions inside of the cell have got a P, potassium, phosphate ions, and then proteins, including magnesium. Most prominent ions outside of the cell have got sodium, bicarbonate ions, chloride ions. So because there is a difference in charge like that, you are going to say that outside the cell you have got more positive charges than negative charges, and inside of the cell you have got more negative charges than positive charges. So this makes a difference in charges. So because I've got a difference in charges, when you put one terminal at the end outside the cell, and then you put another terminal inside the cell to measure if there is voltage, you are going to see that there is voltage here, right? So that is what we call membrane potential. Now, membrane potential itself is simply the voltage that results because of one ion. Sodium itself, because it has got different concentrations inside and outside the cell. Like inside of the cell, you're going to find it is about 14. Outside the cell, it is 142, meaning that the inside of the cell is more negative than the outside. Why am I saying more negative? A 10 or a 14 is more negative than 142. So because of that difference in charges there, we are going to see that there is going to be voltage due to sodium across the cell membrane. Same with other ions. So when you get to add all those different charges due to these ions which are able to move across the cell membrane, that gives you now what we call resting membrane potential. Resting membrane potential is simply the sum of all the membrane potentials of the ions that are able to cross the cell membrane at rest, meaning that there is no abnormality happening in the body. Right? Let's say it is not too hot, it is not too cold. You've not hit yourself, just at normal conditions. So the membrane potential of sodium is positive 61 millivolts. Membrane potential is in millivolts, not volts, because volts could kill a person. Potassium has got a membrane potential of negative 94 millivolts. Chloride ions have got a membrane potential of negative 89 millivolts. So these are some common membrane potentials that we should be close to. All right. So if I get to add all the membrane potentials in red blood cells and in epithelial cells, we are going to find between negative 8 to negative 20 millivolts. In smooth muscle cells, it's going to give us negative 35 to negative 45. In pacemaker cells, negative 55 to negative 65. Sorry for this mistake. In nerve cells, it's going to be negative 70, and this is what we are interested in. In skeletal cells, it's going to be negative 90 millivolts. So we know nerve cells are the ones responsible for reacting when there is a change in the environment or when there is a stimuli. Let's say if you hate yourself or if the temperature is high, receptors are going to be able to communicate with the nervous system for you to be able to react. So in a case when it is very hot, the anterior hypothalamus is going to react so that the temperature can drop. When it is cold, the posterior hypothalamus gets to react. So the permeability of the membrane to several ions is going to lead to the diffusion potential that is going to develop. So because we have got different ions outside of the cell and inside of the cell, there's going to be a diffusion potential. There's going to be a difference. You'll see that the outside of the cell is positive, the inside of the cell is negative. That is a potential difference. That is what we are calling the plasma, or let me say the membrane potential. Now, this is due to many reasons. One of the reasons is the polarity of the electrical charge. Okay, let's say if you have got sodium, let's say we know that overall outside the cell we have got positive charges, and then overall inside the cell we have negative charges. Now, let's say I have got sodium, 50 of them inside the cell, and then only one outside the cell. Now, because the charge overall outside the cell is positive. Even if I've got positive charges inside the cell, I'll not be able to move the sodium to the outside of the cell. Why? Because you already have positive charges there. So I don't need to take other positive charges where it is already positive. So the polarity of the electrical charge of each ion is going to affect the movement. Ions will not only move to where they are low concentrated, but also where there is few of that kind of charge. Also, the permeability of the membrane. Potassium is more permeable to the cell membrane than than sodium. That is because we have got more potassium pumps which are open at rest than we have got sodium pumps, right? Because most sodium pumps are going to require energy, and potassium ions will not. The concentration also of the ions also get to affect the movement of ions across the cell membrane. So if we want to calculate the resting membrane potential, it's going to be 61. Now we should remove the positive or negative. Let me just say positive 61 log concentration of all different ions multiplied by the permeability outside the cell on top. You add them, and then down inside the cell you multiply by the permeability, also the other one inside the cell multiply by permeability. So this one here was supposed to be outside the cell, and then down here it was supposed to be inside the cell. If I put a negative on the 61, then the inside should be on top, the outside should be down. Okay, so any kind of fluctuation in temperature or any kind of stimuli that a body gets to find, the resting membrane potential is going to be disturbed. Remember, resting is when you're at rest. So imagine you step on a nail. So the nervous system is going to respond. Why is it responding? Because the resting membrane potential has been disturbed, and that is what produces what we call an action potential. An action potential is what produces nervous nerve impulses, which you are going to be able to take to the brain and then come back to respond to that kind of pain. So it's basically starts from the resting membrane potential disturbed, and then it goes into the action potential, which are simply nerve impulses. All right. So let's get to consider this question. How do we get to calculate the resting membrane potential? So the resting membrane potential, which is simply the electromotive force across cell membrane, is equal to positive 61. This one is, of course, is in millivolts multiplied by log the concentration of ions outside the cell. Let's start with potassium. Outside it is 1, it is just 4 outside the cell. So that is 4 multiplied by the permeability, that is 20. Go to the next ion, sodium, it is 140 multiplied by permeability. Sorry, I'm not adding. So it is supposed to be summation we add. So that is going to be plus 140 multiplied by 1, and then plus the next one we have got 120 multiply also by 1, and then divided by, we go inside the cell, so potassium we have got 140 multiplied by permeability, that is a 20. Okay, plus sodium is 14, permeability is 1, plus potassium, chloride ions, we have got 4 inside, permeability is a 1. And so this is going to give us positive 61 millivolts multiplied by, let me punch the other side. So what am I going to start with? I'm going to say 4 multiplied by 20, that is 80. And then that will be 80 plus 140 by 1, that is just 140. Then plus 120, that is going to give us log of 340. And then divide 140 times 20, that is going to give us 2800, and then we are going to add 14, then we are going to add 4, so this is going to give us 2818. Okay, so we'll now say 340 divided by 2818, then we'll say log of the answer that we have found. The value that we find, then we are going to multiply by 61. So this is giving me positive 56.02. So which I can simply say positive 56 millivolts. But of course, we know that typically for a neuron, the resting membrane potential is supposed to be about negative 70 millivolts. All right, so this is how you get to calculate the resting membrane.